So let's start the lecture today. In the last lecture, we talked about specifically talking about reinforcement learning with function approximation, and we particularly focus on a simple case called linear function approximation. And we spent quite some time talking about the basic model that is linear MDP, and also specifically focus on one algorithm called least square value iteration, LSVI, which essentially just modify the value iteration, which is the algorithm, essentially the rule of thumb we used for tabular setting, but modified for the linear function approximation by essentially replace the Bellman updates by solving a least square problem. And we particularly spent a lot of time working on the guarantees algorithm and also guarantees for LSVI under the setting of the core set. So it's essentially, you can think it's an analog of the simulator setting in our tabular MDP, where it's in a tabular setting, in a simulator setting, we essentially query all state action pair uniformly, while essentially sweep over all state action pair, while here in the linear function approximation, although we have infinite states, but we just sweep over all the state action pair in the core set uniformly, and we use that algorithm. Essentially, this is similar to a generative model, simulator setting. And we know in the tabular MDP scenario, after a simulator, we will talk about more advanced setting like online setting and also offline setting. So today we will spend some time, a little bit of time talking about how we're going to extend this to the exploration setting or online setting. So in the exploration setting, similar to the motivation in the tabular setting, that is, we're no longer able to just query specific state and action pair. We have to start from the initial states. Okay. So in that case, the strategy that we're going to sweep over all the possible state action pair in the core set no longer available. We can no longer query states. That is, i.e., we can no longer query core sets. So this is a more practical scenario. So in this case, how are we gonna work on this online reinforcement learning problem? So if you still remember in a tabular setting, the whole idea we're dealing with this online reinforcement learning is we incorporate optimism. So here we will try to do the same strategy. That is, incorporate optimism or UCB into LSVI. So this gives the following algorithm. Essentially, how we're going to modify the LSVI with upper confidence bound. So the algorithm is called the LSVI UCB. So for episode K equal to 1, 2, to capital K, do the following, that we will receive initial state S1K. That is the initial state, the state at the first step in K's episode. And then for each episode, we do the following. For step H, from capital H, to little to 1. If you still remember, doing value iteration with UCB, we essentially first doing value iteration per episodes, and then we use the greedy policy to collect the data. So here we will also do the similar thing. We will first do value iteration, but the only difference is now we do least square value iteration. So for each step, we're going to do the following, that we're going to let this lambda h be essentially the Gram matrix we talk about in the least square solution. Summation tau from 1 to k minus 1. Phi h tau inverse plus lambda I, where this phi h tau is defined to be phi sh tau ah tau. Okay. It's the feature map of the state action pair we visited at step h at TOS episodes. And this lambda I is essentially the regularization we talk about. Because we're in an exploration setting, we're no longer guaranteed this is full rank. So we're adding a small regularization to make sure the matrix is full rank. And then we essentially just solve for the least square solution, which, if you still remember, the solution of least square value iteration is this Gram matrix, take it inverse, and then summation tau from 1 to k minus 1, phi h tau, and rh, sh tau, ah tau, plus max A, Q, H plus 1, SH plus 1 tau, and A. Next step. Okay. This is precisely the solution of the least square value iteration. That is, we have this Gram matrix inverse and then the remaining thing. If you still remember how we derive the least square, this is like how we calculate the weights. So nothing fancy so far. So the most important thing now is how we're going to assign the Q value. Because if we directly use this weight vector times the feature vector we have, the phi, then this is like solution of least square. But now we're seeing we need to add a UCB. We need to add an upper confidence bound. So in the Q value updates, we do the following. That is Q value will be assigned again to be the minimum over h. That is truncation. If the value is greater than h, we will truncate it to h. And then WH transpose phi. So this is a standard linear function solving by least square value iteration. So the major difference is we will add a bonus. Okay. So the bonus is in the following form. That is beta, some constant, scalar beta, times a quadratic form, which is phi, feature vector, transpose lambda h inverse transpose phi. Okay, so this is like the most important thing. This is the bonus we have. So the new Q value will be some linear function with a weight vector solved using the least square value iteration formula, and plus a quadratic form as a bonus. Okay, so quadratic form has some scalar, and we have the phi transpose phi. So this is a quadratic form on phi, and the only important thing is we have this Gram matrix lambda inverse. We will talk about why we choose this specific bonus later. So this more or less finished the first part of the algorithm, essentially how we're going to do the value iteration based on the previous data. Then the next step is very straightforward. So the remaining thing is for step h from 1 to capital H. We do the following, that we will take action AH, K. We take action at step H and K's episode to be the greedy action of the Q value we computed earlier. And then we observe the next states. Okay. So the overall algorithm has two parts. The first part is essentially this part, which is LSVI with bonus. And the second part is this. This is like execute a greedy policy. So the overall algorithm is relatively straightforward. As I said, the only major difference is like you add a bonus here. And the bonus is specific form for the linear function approximation. And the remaining is following the generic like prototype or like the generic framework of like value iteration with UCB. Any questions for this algorithm? Yes.
Just making sure, like phi is something that you intrinsically know before going into the algorithm? Or?
Yeah, the phi map is known, is a feature map that is known. Yeah, for linear function approximation, we always assume we know the map, but in general, it's right. Like when you do dpile, a lot of times you also need to learn the feature map. That will make things a lot more complicated. Okay. So now the question is why we choose this specific type of bonus. Okay. So why we use this phi transpose lambda inverse phi as bonus. The reason is pretty specific to like a linear function approximation, like this linear thing. So you can interpret this as roughly something like 1 over square root of n phi. Okay. Just remember in the tabular setting, what we have for the bonus setting, bonus function is 1 over n. N is like the number of times we observe that specific state action pair. So in the linear function approximation, you can think this is roughly 1 over square root of n, where n is the number of times effective samples you see in phi direction. Okay. By effective samples, we mean like, because this is like a linear approximation, so you should not just say, only when I observe the direction that exactly equal to phi, I will count as I observed it previously. Like because this is linear, so anything close to this phi direction, you can count it as 0.9 samples in phi direction or 0.8 factor, like samples in this phi direction. So this is about effective numbers of samples in this phi direction, and this effective number is counted by this matrix inverse. And we'll say specifically more like why this reduced to the, like why this phi inverse, this specific form like square root makes sense. So I think understanding more concretely, we should first consider the special case of tabular MDP. Where in the tabular MDP, we know the feature space, this capital phi, essentially all the possible linear feature vector we have is just the EI. Okay? It's just the basis vector where I is from 1 to D. And in this case, each I corresponds to an SA pair. So in this case, this lambda matrix is essentially just a summation of all the previous feature vector we have seen. That is a summation of phi j transpose. And then we can group all the feature vectors that are corresponding to the I spaces together. And so it's a summation I from 1 to D times how many times we have observed this EI in all the past data times EI transpose. This is how many times. We have observed EI. So in that case, when we look at the bonus function is always in form of we have 5 lambda inverse phi. So that is, for example, phi is some EJ, because the feature vector is always just the basis vector, and EJ lambda transpose, lambda inverse EJ. And because we know this lambda is of this form, so we know lambda inverse is of the form that is summation I from 1 to D, 1 over Ni, EI transpose. Okay? And this bonus function is exactly equal to 1 over Nj, which corresponds to the, essentially corresponds to the confidence, the like Princeton bounds we have for the tabular setting. So this is like a very special case because in a tabular case, all the feature vectors are orthogonal, so that essentially only the exact same basis vector will increase your count, and anything else is because it's exactly orthogonal to you, so they won't increase your effective number. But in general, beyond linear setting, beyond tabular setting, this phi I feature vector may not be orthogonal. So any previous observation so that this phi I transpose phi is not equal to 0. So as long as this phi is not orthogonal to phi, will increase the effective number of phi by a number in 0 to 1. So this is more or less an intuitive understanding of why we're going to use this type of bonus function. And the more rigorous mathematical reason, like stem from the linear bandit scenario, I think as we said in this class for a lot of times, bandit is like a simpler case for MDP without any states and a transition. So it always serves as a toy case or a simpler case to consider. And it turns out there's a model called like linear bandits. And the linear bandits, they also study the UCB algorithm, and this is like specifically designed you can use for linear bandits. So you can think this bonus is like what we borrowed again from this bandit literature and plug it into like a reinforcement learning and make it still work. So we'll directly talk about the guarantees for such an algorithm. For any linear MDP, again, we restrict ourselves to the model of linear MDP, which is still a bit restrictive that require both reward and transition to be linear. Then we say with probability greater or equal to 1 minus p, the regret of LSVI UCB is the following. That we have regret k less or equal to c times square root of d cube h cube t iota squared, where again this iota is log dt over p. And this is the result stated in terms of the regret. And you can still use the similar thing earlier we talked about. We can convert any regret to sample complexity by online to batch conversion. So you can convert this as well to some sample complexity using that theorem. So I will just make two quickly remarks. So the function approximation setting will be slightly different from tabular setting where we care a lot about the rates. Where function approximation setting, we will talk more about what is the setup and what is the type of guarantees we can get. And we leave the rates, like those detail rates, to like some lecture notes or like more specific papers. So I think high level, the most important thing we observe, the improvement of this LSVI UCB versus the previous, the core set thing, is now we no longer assume given the core set or we can query core set, okay? Given or access to. We use optimism to explore. So this improvement is quite significant. That is, we no longer require access to a simulator, and also we don't even care about whether we exist to some core set or not. We can directly give this. And in fact, the result, if you remember in LSVI with core set, we still need to depend on some one norm of the core sets, that L factor. Well, here, this is completely independent of this L factor. So that is, I don't really care about whether you have good core set or not. I can always make this guarantee. The second important thing we already emphasized in the core set thing, we no longer no longer have SA dependence. This is always important in like function approximation. We have replaced them by D, by dimensionality in the linear setting. Okay.
What is the last one?
Oh, why is the last one right?
Them by.
Replace them by D. Dimensionality. You can actually think dimensionality plays a role as an SA, because like in a tabular setting, when you reduce to a tabular, essentially this D is equal to SA.
Okay.
But in general, you can think D is like more general. It's not necessarily SA. Even for infinite S, you can have some fixed D or small d. Okay. So the proof is a lot more involved. You can imagine it's like basically a combination of upper confidence bounds and the least square value iteration and some exploration like regret analysis. So we'll leave it to the paper, to the previous paper. It's in the provably efficient reinforcement learning. With linear function approximation paper. By me and a few other collaborators in 2019. Any questions so far about this LCVI UCB thing for optimism? If not, we'll go to the next topic. That is, we'll again talk about linear function approximation, but we want to talk about beyond linear MDP. So this goes back to a question we raised earlier. We're saying linear MDP is quite a strong assumption that we have assumed both linear transition and linear reward. But for a lot of times in practice, like when we do deep IO, we only care about, we kind of like approximate the value function by linear function. Yes, please.
I was just wondering, can you also do like LSVI with like pessimism for offline settings? Or?
I think so. People also do that kind of variation in the paper, yeah. Yeah, let me check. I think that has been done. Okay. So the question is whether we can relax assumption. If in the end all we care is like we approximate the value function by some linear function, like we don't really care about whether underlying MDP is linear. Hopefully we can deal with some like more generic MDP as long as we just do value is equal to linear function and we can still make it work. So people have been thought about this question for a while, and I would think there's the one type of result I would like to introduce, which I really feel like they're quite elegant, and it's this slightly more general class. Let's temporarily call it like linear completeness class. I think I like this class because the algorithm solution eventually we introduce is like pretty generic, and we will see it can generalize to the general function approximation. It's very elegant. So let's talk about what is this like more general condition is. So remember whenever we talk about the linear function approximation, we really talk about the linear value function class in this class. Okay. So it's specified as f is the function class that is consider all the linear function in the form of phi transpose w for all w in R. Okay, w is a vector in R. So this is essentially all the possible value vectors, the value functions we consider. So the assumption of this linear completeness class is we basically make two assumptions. The first one is realizability. Realizability in terms of, okay, remember now we are beyond linear MDP, so we no longer assume we no longer assume we have a linear transition or reward, but we need to have replace this linear MDP with some more abstract assumption. Hopefully, we can cover more applications. So the first one is realizability, which is quite weak, which just assume the optimal Q value, Q star, is in F. That is saying we don't really know whether underlying MDP is linear transition or nonlinear transition. We don't care. All we care is the optimal value is linear. And the second assumption we have is called essentially the completeness. That's why we call this setting as like linear completeness. So what we say is this T star is the Bellman optimality operator. F is inside F. Okay, so what does this notation mean? So remember, this T star is the Bellman operator. It's the Bellman optimality operator. So for any function of a SA, that is a Q value function, we say the T star F. T star essentially map a function to a new function in the SA. And we say this is equal to RSA plus max A transition F. And this Fs prime A prime. Okay. It's just the Bellman update. So it maps a function of a SA to a new function in SA. Okay. So what this completeness means, for any linear value function, if you apply the Bellman operator as defined here, Bellman optimality operator as defined here, it remains to be a linear function. So it remains in this class of linear function. Okay. So that in that sense is like completeness. That is, by applying the Bellman operator, a linear function will remain to be a linear function. This is like the whole assumption of this linear completeness. We'll first check very simply that linear MDP is a subset of this linear completeness. So the most important thing is we will make sure that after applying the Bellman operator, a linear function will be mapped to a linear function. This is relatively straightforward in the linear MDP because in the linear MDP, both reward is linear and also the transition is linear. So this part will guarantees. Sorry, I think I got it wrong. This is max inside. Max A prime. Okay, this is a Bellman operator. So because the transition is linear, so this basically says whatever this is, I don't care. As long as I'm applying the transition, it becomes linear, and this is linear, so it remains in the linear. So it's easy to check. Easy to check that both conditions in the assumption hold. First assumption is also quite straightforward. And I think first assumption is actually a bit redundant. If you kind of like already says the value function in the last step is 0, and you also see 0 is in this f, then this completeness will basically guarantee realizability in some sense, because the optimal value function is this t star. But you can basically show the same thing there as well. I think first condition is actually even simpler for linear MDP because in the linear MDP, we basically already shows the Q value for any policy is linear. So the Q star is, of course, a linear function. So that's pretty. So, of course, whenever we introduce some new condition, we would like to at least see one example that is beyond the original linear MDP, but still in the linear completeness. So there's another example which is very important in the control literature, which actually following this more general class, but not in this original class. So that's called LQR. This is called like a linear quadratic regulator. This is like one of the very basic model in the control literature because in the control, I think people also do like linear control, and this is essentially the very basic model for linear dynamics. So we'll motivate this important model by like a real application. Let's look at the application, which, for example, we want to control the height of some robotic helicopter. So in that kind of case, let's just recall what we learned from the physics in high school. If when we want to control the height of velocity, for simplicity, we no longer care about some spin or some rotation, so we just look at the height. So in that case, let ht and vt denote the height and the velocity at time t. So we need to calculate like how much force we need to add to the helicopter to either like raise the height or like reduce the height. So in that case, whether we want to control the force, which is essentially equivalent to, we also want to control the acceleration. Okay. Because by Newton's second law, like force will directly related to acceleration when mass is fixed. So according to the Newton's second law, we can essentially write the dynamics as the following. A discretized version. We can write the following dynamics. That is the height at t plus 1 time, and also the velocity at t plus 1 time is roughly equal to 1 and tau. Tau is essentially the time interval. And 0, 1 and times ht vt. Okay. So up to first order, the calculation is the height at t plus 1 time is the height at t time plus some small interval tau, the time interval times the velocity. Okay, this is like the change in height. And also the velocity up to first order is just the original velocity. And then we need to add a second order correction term, which is 1/2 tau squared and tau times the acceleration, which is at minus g. And the goal of such a problem is to find the best policy essentially the policy is we can control the acceleration conditioned on the state, where state is here is just the height and the velocity. And so that we will find such a policy, we can maintain the height so we want to maintain a helicopter at the height h star as best as we can. And we want to do that with the least amount of power. So this is like a very natural objective. That is, we want to just maintain it at height h star, and we want to use as least amount of power as possible. We don't want to like make it oscillate a lot, like wasting a lot of power. So in terms of mathematics, you can essentially formalize this as minimizing some objectives. So we just want to minimize summation t. T is the time that ht minus h star squared. Okay. This is the first objective. We want to maintain the height of helicopter as close to h star as possible. And then we want to use the least amount of power as possible. That is, we can essentially adding some coefficients times at squared. Okay. So at squared kind of corresponding to the energy we use for the helicopter. So this is essentially the objective we can consider for this control problem. So this application motivates a generic class of control problem, or MDP, called LQR, which essentially you can think is an abstraction of this type of application. So for general LQR, you can essentially abstract what we have here as a, you can consider an abstract version, where for this problem, state becomes something like xt equal to ht vt, and let's just have some dummy 1 here. This is essentially all the states we have for this LQR problem. And we also have action. In this case, it's basically we can choose the acceleration or choose the force, which we use a ut to denote action, which in this case, action is just at. So LQR is in general the type of following problem that we have. Sorry. LQR is a generic type of problem like this. It's an MDP. Again, we have a state action. All we need to specify the set of state, set of action, transition, reward, and horizon. Let's say horizon here is t. So the state set here for general is RD. Okay. So it's a vector in some d dimension, so which is similar in the helicopter. This is like a 3-dimensional thing, where here in general we can do a d-dimensional thing. And action set is again also d-dimensional thing. Let's say d prime, so that dimensionality can be different. So we have both state set and action set as a vector set. So the important thing now is we need to specify what is a transition. As we said, the LQR is essentially one of the simplest control models, so it assumes a linear transition. Linear transition means we will assume xt plus 1 is the state, is a new state in the t plus 1 time, is equal to A times xt. A is a matrix, okay? In d by d, plus b times ut. B is again a matrix in d by d prime, and plus some noise, wt. So this is a linear dynamics. And this is generic LQR, assume this type of form. And we can see this application is in general falling to the LQR because if we make this as xt plus 1, this is xt, and this is ut, and this is clearly following the linear dynamics, okay? Linear in terms of this state and this action. And finally, we'll also talk about the reward. So in the LQR model, we always assume the instantaneous reward, which is again defined as a function of state and action, is a quadratic function of both state and reward. So this is a Q X transpose QX plus U transpose RU. So this is essentially this is the cost. Within the bracket is the cost. So negative cost is the reward. We will use the MDP language, so it's called reward. So we can think in the helicopter case, we want to minimize this. So we want to minimize some cost in the negative of reward. And we see the cost is exactly the quadratic form of the state, which is HT, part of the state, and also the action. So this, again, following the LQR model. Yes?
Wait, since it's like HT minus H star, is there not some term that's linear in HT?
Oh, and also we kind of include a 1 here. The reason we include 1 here is because we can make it a quadratic in terms of HT and 1. Yeah. I think the same thing here when we have the G here. G is also a linear term. So that's why we kind of augment the states by additional some dummy things so to include the constant thing. Otherwise, like you're right, you also have like linear term and zeroth order term. But here for simplicity, let's just say everything is quadratic. Okay. And the important thing here is we need to assume both Q and R are PSD matrix. So basically now we have 4 parameters. We have AB in the dynamics and the QR in this reward. So this 4 matrix specify the transition and the reward. With the first 2 AB specify the transition, the later 2 QR specify the reward. And those 4 matrix thus specify the LQR. So hopefully you're clear with what is the LQR model. This is like the abstract LQR model, which has this linear transition. In this definition, it's like different from the linear transition in the linear MDP, but it's this form of linear transition and also the quadratic reward. And this helicopter stuff is one example which show why we kind of like want this quadratic reward, why this linear transition makes sense. So once we have understand what is LQR, now we have the following claim that LQR satisfies the linear completeness. But it's not a linear MDP. It's a very good practice to check the definition by plugging those those directed conditions and check whether those definitions or those assumptions are true. So we'll leave this to homework 3. Yes.
It's like given
Sorry, could you say it again?
Or like with the transitions, like out of the probability transition matrix, I'm just thinking about how like Bellman would work for that, and like the expectation of the next state is basically just axt plus but, right?
Yeah.
Okay.
Yeah. For some linear function, yes. But I believe the value function for LQR is actually not linear function. It's actually a quadratic function. Sorry. I think I also want to say a little bit more. So it turns out it's essentially a little bit hint. So by linear completeness means we need to essentially augment a little bit the feature space. So in general, LQR, value in LQR, is a quadratic in both x and u. So this seems like it's irrelevant to like a linear complex or linear MDP. But basically what we can do is we can do some augmentation that we can do the linear feature map. This is what we want for the linear feature map, equal to something like a vectorized version of XX transpose, vectorized version of UU transpose, and also vectorized version of UX transpose, and X and U and 1. So if we make this as new thing as a feature, then anything quadratic in X and U is linear in phi. Just because you essentially expanded out this vector thing. You understand what I'm saying? So in that sense, like basically any matrix X transpose MX, you can write it as a trace of M times XX transpose. The trace of M times XX transpose essentially is just a vectorized version of M. Essentially, we can like put the entire matrix M as a vector. We can like make this a D by D matrix as a D square dimensional vector in a product with vector version of XX transpose. So that's why it's, in this sense, this thing, although it's quadratic in X, but it's linear in XX transpose. Okay. So when we talk about LQR as linear completeness or linear MDP, we talk about it in this feature vector. And we will talk more about this in the homework. Okay. So now, after we introduce the new generic class, as in this class, what we always do is like we introduce the class of problem, and the next thing is we need to design a new algorithm to solve this class of problem and then provide guarantees. So that's why we said the next step is we're going to talk about what kind of algorithm can solve this. And unfortunately, the original LSVI with UCB algorithm no longer able to handle this linear completeness scenario. I think the reason is do a lot of specific this function, like bonus, adding in this specific bonus function, where we will talk later, like what's the major difference from this new algorithm. So the whole idea of the new algorithm that able to deal with the more generic class comes with some trade-off. It's called the global optimism. You use the global optimism. By saying this is global optimism, we're essentially referring the previous way of adding bonus as something like local optimism. So we will see more clearly what is global optimism, what is local optimism when we write out the algorithm. But for now, let's just say the whole new idea is this global optimism thing, and the entire algorithm is evolved on that. And this actually comes with some trade-off. It's not always gain. There is something loose in this thing. So the new algorithm is called Elena algorithm. It's introduced in the following paper with the title, Learning Near Optimal Policies with low inherent Bellman error. By Zanet et al. In 2020. So I cite the paper here because we won't be able to talk about the proof. And if you're interested in check out how it works, and you feel free to refer to this paper. So the algorithm looks like follows for episode k from 1 to capital K. Do the following. That we will receive the initial state again. S1K. We construct the following confidence set. Okay. So the confidence set is the set of theta parameters. Okay. So we have one confidence set at per episode. Okay. So this is essentially the confidence set we construct as at a case episode. So confidence set is a set of weight vectors for values, theta 1 bar to theta h bar. So you can think essentially theta 1 is the weight vector for essentially if we still use the linear value function. So that means for value at each steps, we just need a weight vector. So theta 1 bar is a weight vector for the Q value at the first step, and theta h bar is the value vector for theta value at each step. Okay. So those are weight vectors at each step. So you can think this is a confidence set of this weight parameter. You can also think this is a confidence set as a value function, okay? Because theta directly determines the value function if we just directly choose the linear function. And the weight vector is essentially a set of weight which satisfy a couple of constraints. The constraints is relatively simple. It says I only consider all the value function, all the weights, so that it's not very far from my least square estimate. Okay. In terms of this lambda h norm. Okay. So we'll talk about this later. So here we need to introduce a bit about what is this norm and what is this the theta hat. So basically the notation here is, let's say for any vector, this phi lambda norm square means we have the phi transpose lambda phi. This is how we define it. So this basically we have this vector, and transpose with this matrix lambda h and times this vector. And by lambda h, we do mean the gram matrix we talked a lot about earlier, which is tau from 1 to k minus 1. This phi h transpose, phi h tau transpose. Again, all the previous feature vector and sum together and plus some lambda I, which is small regularization. So this is the same gram matrix, and this theta hat thing is just a least square solution, which is again this phi inverse, and the summation tau from 1 to k minus 1, phi h tau, and rh tau plus max A, theta h plus 1 bar transpose phi sh plus 1 tau A. So this is the LSVI solution. Using theta h plus 1 bar as value in the next step. Okay. So after seeing this, we now see this confidence set is not as simple as we originally thought, because this theta hat cannot be computed independently for a different step. This theta hat actually depends on the choice of theta h plus 1 bar, which is again a parameter here. So this constraint, you cannot just decompose this constraint into a constraint of h steps. They are not decomposable. They're kind of like some nested constraint that will apply to all of them. So this one basically is a constraint for both theta bar h and also theta bar of h plus 1. This is a function of theta bar h plus 1. So every constraint is essentially a vector, a weight vector for the neighboring steps that depends on theta h bar and theta h plus 1 bar. So essentially, we're saying this confidence set is a set of weight vectors that satisfies all the constraints. So this is like nested constraints. So once you understand this confidence sets, the remaining thing is like very straightforward. So all the remaining thing is we compute. We do optimistic planning. That is, we compute the optimistic value function. Theta 1 bar, till theta h bar to be the argmax of this theta 1 bar to theta h bar in this theta k. Max A phi S1K A theta 1. So you can think this part is essentially my value at the first step, looking at S1K, if we parameterize by theta. So this essentially says I just find a set of parameter in my confidence set so that I can maximize the value function of the first initial state. And then we just do execution. It's again greedy execution. So this is like, you can think this is a whole part is like a value iteration, and then we do execution to capital H. Do the following, and we will take action. HK. Which we give it as our argmax A of phi shk A transpose theta h bar. Yes. Question?
Wait, so the confidence set, like all the different values in there, like tuples of these weight vectors that like, are you getting those from some data or like they're just like any kind?
Yes, you're getting some from data because those are the previous data, right? This lambda h and theta h hat actually depends on the previous data. This depends on like all the weight vector, all the feature vector you have observed previously. This tau is again the same thing in LSVI, essentially the previous feature vector you have observed. And this is also the feature vector observed, reward you observe, and the next state you observe. Yeah. So the whole estimation, this least square estimation, depends on both theta and theta bar h plus 1.
So theta k, like the actual whole set might like be like an infinite number of entries or whatever. Like it's not just like
A lot of constraints. H different constraints.
a lot of constraints, but like there's still like it's like a real space with like not just discrete entries, right? Like
Not, yeah, it's a real. You can think in general, it's like, at least like in a linear setting, it should be some like subset of the space. Yeah. So the whole idea is, again, just instead of using data to directly compute the upper bound on the value function, like in the LSVI UCB, here we kind of like did it a little bit implicit. We kind of like say, so after we collect all the data, we use data to construct some confidence set. By this confidence set, we're more or less certain the optimal value Q theta star will be inside this confidence set. And we kind of constructed this confidence set in this specific manner as a nested constraints, so that we will see later it's very important, it's very sharp. And another whole idea, like why we talk about the global optimism versus the local optimism is here we explicitly compute the value function, that is theta 1 to theta h, which only maximize the V1. V1 is the value at the initial step at S1K. So we never say we're gonna optimize over any middle value or anything. Remember in the tabular setting or in the least square value iteration, we can essentially guarantee for every state our value function is like upper bound. Here, we no longer require that. We only require in the very beginning, this is an upper bound. This is like an optimistic value. We want to find argmax. We don't care about anything in the middle. In the middle, we don't want it to be like optimal or anything. So this is why it's called global optimism. So we will talk a little bit more about what do we specifically mean by those, like what is a major mechanism difference. So in the global optimism, the most important things we only guarantees upper bound in total reward. Which in the sense, we don't guarantee the V1 bar we find here is an upper bound on the V1 star, specific initial states. While in the local optimism, we essentially guarantee its upper bounds. For all steps, all states, which essentially says for any states and any h, we need to guarantee this VH, whatever VH bar, let's say, VH bar S is greater than V star HS. Okay. So we note this is true for both VI UCB in the tabular setting, and also the least square value iteration is also in that setting. Remember, we adding bonus in every step, so that we can guarantee the value function is like an upper bound. Okay. So in general, this poses a lot of, this is like pose a strong constraint. This is a comparatively a lot weaker constraint. And remember how the optimism works. Optimism, essentially, we need to have two parts. So optimism, typically, when we talk about optimism, we're talking about bonus, or we're talking about adding some additional thing to the original value. So we want optimism bonus to be large. Okay. So we want two things. One is a bonus is large, so that we guarantee the upper bound. The second thing, we also want the bonus to be small, so that we understand that whatever the bonus we're adding is actually negligible, so that the regret is small. Okay. If we're adding too much bonus, we're essentially paying this bonus in my regret, and that we're going to hurt the regret. Okay. So those are conflicting goals. In order to ensure the upper bounds, we want the bonus to be large, and in order to ensure the regret is small, we want the bonus to be small. So essentially, you can think the local optimism put a lot of constraint in this upper bound part, so that whatever the bonus you're adding, eventually you can like blow up the constraint set to be so large, you can no longer make the regret small. On the other hand, well, when we do the global optimism, we put a lot less constraint. We don't put that many constraints. We only require the first value to be large, to be the upper bound. So in that sense, we can allow much smaller bonus, and reflected in mathematics is we construct a very tight confidence set. The confidence set is written in that way, so that we can make sure the regret is small. Okay. So the global optimism, we can have small bonus and a small regret. So this is essentially the benefit of why we want to remove some unnecessary constraints when we do the optimism. That's why we kind of like move from local optimism to global optimism, just because we want to make the regret to be small. And it turns out for this like a linear complete case scenario, this local optimism regret is so large so that it doesn't even make sense. It's something exponential in h, while the global optimism will give you something polynomial in h. And finally, I just want to comment that one single thing is this global optimism does not come with free lunch. Okay. The global optimism has one drawback, that is it's computational inefficient. you can more or less observe from this confidence set. This is like a nested constraint. So this confidence set has no clean way to represent it other than like basically written all the function and there's like a very complicated optimization within it. And now you want to just optimize with this like weird shape of confidence set. So the computation is very intensive. It requires you like search over the entire function space to get this very sharp bonus. Well, for the local optimism, it's actually computational efficient. Like LSVI UCB is an efficient algorithm. Okay, so yes, I guess we will, it's about time. We will briefly talk about the guarantees for this linear in the next lecture, and then we move to the general function approximation.